In calculus, we often want to know what happens to a function as its input x gets extremely large or extremely small. This is called finding the limit at infinity. We use this notation, the limit of f of x as x approaches infinity. The answer to this question, if it's a finite number L, tells us about the function's long-term behavior. It defines a horizontal asymptote, which is a horizontal line, y equals L, that the function's graph gets closer and closer to. The most important tool for these limits is understanding what happens to fractions like 1 over x. Think about it. 1 divided by 100 is small. 1 divided by 1,000,000 is tiny. As the denominator x gets infinitely large, the fraction gets infinitely close to 0. This rule holds true for any constant c and any positive power of x. This is the foundation for solving more complex problems. Let's look at our first example. We want to find the limit of this rational function as x approaches infinity. The trick is to identify the highest power of x in the denominator, which is x squared. Then we divide every single term in the entire fraction by x squared. Now we simplify each term. 3x squared over x squared is 3. 2x over x squared is 2 over x, and so on. Using our key rule, we know that as x approaches infinity, any term with x in the denominator will approach 0. So 2 over x, 1 over x squared, 4 over x, and 7 over x squared all become 0. This leaves us with the final answer of 3 over 5. This means the function has a horizontal asymptote at the line y equals 3/5. Now for our second example. Here, the degree of the numerator, which is 1, is less than the degree of the denominator, which is 2. We use the same strategy. The highest power of x in the denominator is x squared. We divide every term by x squared. After simplifying each term, now we apply the limit. Every term with an x in the denominator goes to 0. This simplifies to 0 divided by 1, which is 0. So the horizontal asymptote is at y equals 0, which is the x-axis itself. In our final algebraic example, the degree of the numerator, 3, is greater than the degree of the denominator, 2. Again, we follow the same process. The highest power in the denominator is x squared, so we divide all terms by x squared. Simplifying this gives us x minus 4 over x, divided by 2 plus 1 over x squared. When we apply the limit, the terms 4 over x and 1 over x squared go to 0. We are left with the limit of x divided by 2. As x approaches infinity, x divided by 2 also approaches infinity. When the limit is infinity, it means the function grows without bound. Therefore, there is no horizontal asymptote. Limits at infinity have practical applications. Let's consider the average cost of production in economics. Suppose the total cost to produce X items is $5,000 in fixed costs, plus $2 per item. The average cost per item, A of X, is the total cost divided by the number of items, X. To find the long-term average cost, we take the limit as X approaches infinity. We can split the fraction 5,000 over X plus 2X over X. This simplifies to the limit of 5,000 over X plus 2. As X goes to infinity, 5,000 over X goes to 0. The limit is 2. This means that as the company produces a very large number of items, the average cost per item gets closer and closer to $2. The initial fixed cost becomes insignificant. To summarize, when finding a limit of a rational function as x approaches infinity, you can use a shortcut by comparing the degree of the numerator, n, and the denominator, m. If the degrees are equal, the limit is the ratio of the leading coefficients. If the numerator's degree is smaller, the limit is always 0. And if the numerator's degree is larger, the limit is positive or negative infinity, and there is no horizontal asymptote. Remember, this is a shortcut. The method of dividing by the highest power of x in the denominator is the formal proof for why this works. Understanding limits at infinity is crucial for analyzing the long-term behavior of functions in many fields of science and economics. Thanks for watching.